Hello and welcome to another video. Today we're going to be working on maximum twin sum of a linked list. And I think this problem description isn't the best, so I'm going to try my best to describe it a little bit better. Essentially, we have a list of n times 2 nodes, so it's going to be an even node list. So let's say we just have like 6 nodes here. What we are asked is we are actually asked to find the maximum sum between every single pair of nodes, and the pair is like the first node and the last node, and then the second node and the second to last node, and so on. So like this would be a pair, this would be a pair, this would be a pair, and so on. And so it's like, you know, if you have to label this as like 1, 2, 3, and then from the back 1, 2, 3, right? Kind of like that. And so for this first example, now that we understand kind of what it's doing, is we have a, so we draw this, 5, 4, 2, 1, and so they're asked like what's the maximum sum. So here's 6 and here's 6, so the maximum sum is 6. And now in the second example we have 4. I'm not going to draw out the circle for the node. I'm just going to draw out the node itself. So here we have 7 and we have 4, and so our answer is 7. And finally for the last one we have 1 in 100,000, and so that's just going to be 100,001. Okay. Now that we know kind of what we're asked, let's figure out how we would do this in an efficient way. And I'm actually going to redraw this. So let's say we have our nodes, and I'm actually going to draw them by colors, right? So we're going to have 6 nodes again. So let's say we have node 1, and then node 1 from the end. Then we have node 2. Maybe I'll draw some more if I could fit it. We'll see. 2, then node 2 from the end. I think this looks good with 6 though. So we have node 3 and node 3 from the end. And obviously their normal number is going to be like 1, 2, 3, 4, 5, 6, and so on. But this way it kind of makes it easier to see the pairs. So the way we need to do it is we need to actually be able to compare these 2 nodes, and then we need to compare these 2 nodes and these 2 nodes. But how do we do that, right? Because our linked list is actually just going this way, right? So we can't have access to the first and last node at the same time, or even if we could, you know, but okay, let's say we do have access to these, like I guess we could, right? We could like traverse to the end, but then we can't traverse backwards here to get to this node. So one thing you could do, like what would be the brute force approach? Brute force approach would be something just have an array, right? And just get these values, like traverse the list, go through the values, put them into the array, right? And so it'd be like value 1, 2, 3, 4, 5, 6. Then you just have a pointer to each one and you just add them together, right? So you take these 2, you take these 2, you take these 2, and so on. So what's going to be the time and space here? So to make this array, that's actually going to be go of n space. And so that's not ideal, so we're going to try to do it in constant space. But this is going to be like the brute force approach for this problem. For linked list problems, you can't really get too out of line in time and space complexity, right? It's pretty hard to get like an n squared or something. I mean, I guess you could technically get an n squared. Yeah, so an n squared would be like, you know, the length, and then like, let's say we get to this node and we know like, okay, we need to go 5 to go to this node, so we just traverse down 5 to get to that node. Then we go to this node, then we know we need to traverse whatever to get to this node. So I guess that would be n squared, so that would be even worse than an n space. That would be n squared times 0 space, or 1 space. But how do we do this in a better way? And so there is actually a better way to do this, and it's going to involve 2 steps. The first step is going to involve finding the middle of the list. So it's always going to be an even list, so you actually want this node here. Once you have this node here, let's just call that whatever. Essentially what we need is we need this node, and then we need this node. So let's just call this node like list 2 or whatever it is. But essentially once you have these 2 nodes, so just call these like nodes A and B. Once you do have these, then you can actually split here. You can break this. And now you have 1, 2, 3, 3, 2, 1. And now, notice, now if we reverse this, right? If we reverse this, it's going to look like this. We're going to have 1, 2, 3, right? So if we reverse this part of the list, and we compare it to this part of the list on the left, it's also 1, 2, 3, right? And now it's pretty straightforward. Both these lists are the same length. And we have a node here, we have a node here. We can just compare them. Then we go to the next node and go to the next node, compare them. And then go to the next node, go to the next node, compare them, right? That's going to be O of n. So that's going to be our algorithm. We need to split it in half, and then we need to reverse the second part. Now, how do we split it in half? So there's a few ways you could do it. You could just take the length, or you could have a fast and a slow pointer, right? So let's think about that. How would we do this with a fast and a slow pointer? And let's try to figure that out. So let's actually clean this up a bit. Let's get rid of all of this. Let's get rid of all this. There we go. So ideally, we want our slow pointer to be here when the fast pointer is somewhere, right? Okay. So let's think about how that would go. So if let's say we have a slow pointer here, and we have a fast pointer here. So what would happen? So the fast pointer would go, like, what would be our conditions? We'd go 1, 2, maybe 3, maybe. But we know that our list is at least 2 nodes. So we can actually have, and this is kind of the things you need to work out with a slow and fast pointer, just put it in a bunch of different spots and try to figure out, like, what would happen if I put it here? You know, what condition am I looking for? And you can do it this way, right? So let's just say, for example, we actually did put it here. So how many times would we want our slow pointer to move? We'd want our slow pointer to move once, twice, right? To be in the ideal spot. So that means we want our fast pointer to move twice. And so for the fast pointer to move twice, it would actually be over here. And then you would have to say, like, your condition would be like if fast.next and if fast.next.next or something like that. So you could do it that way. That would totally work. Or what you could do is you can actually put the slow pointer here and then the fast pointer here, and we're guaranteed to have 2 nodes, right? And then we can just check for if fast.next, right? So what's going to happen here is after one iteration, the fast pointer is going to move over here, and the slow pointer is going to move over here. And then after 2 iterations, the fast pointer is going to move over here, and the slow pointer is going to be over here, which is right where we want. And then we can just check if fast, or we can just check for the fast.next, right? Essentially, it's guaranteed to be on the last node eventually, because if you think about it, it's going to be on even nodes, right? So if this is like 1, 2, 3, 4, 5, 6, you always have an even number. So if it starts on node 2, it's always going to be at the last node at some point. So we can just check if fast.next. So let's write down our steps. So make slow pointer equals head, make fast pointer equals head.next, and then while fast.next, move them both up, right? And so now that we have the slow where we want, we actually need to save this node somehow. So let's just call this like head2 or whatever we want to call it, right? So we can just call it like head2 or whatever you want. Okay, so now let's just put that over here. It's actually right here. Okay, so let's try to put that over here. There we go. So for, we're going to say head2 equals slow.next. Then we are going to cut them, right? So we're going to say slow2.next equals none, essentially. And now we made a split here. And now we just need this head2. We're going to get the list reverse here. We're going to get the head of this list, and we're going to have the head of this list. And then we're just going to go one by one by one and compare the value. Okay, so we're going to take this 3, 2, 1. We're going to take this 3, 2, 1 list that's on the right side. We're going to have a head 2 over here. And then finally, you know, if we have a head 2 in like a previous, once you do the reversals, the previous is going to be the new head of the list, just like a normal list reverse. So that part should be pretty straightforward just by doing a normal list reverse, which is like a LeetCode easy problem. Okay. So that's how we do that. And now our previous is the new head of the list. And then we have the original head. And now we can just compare values one by one, right? So this is the original head. Now we just compare values, like we compare the 1 and the 1, we move them, and so on. And because these 2 lists are the same length, we can just compare them, and then we can just take the maximum there to be the result, and then once they're out of bounds, we're done. Okay, so now we have enough to be coding. And hopefully you're going to do this right. So what we need is first a slow and a fast pointer, right? So we just say slow, fast equals, and we remember we said head and head.next. And we're guaranteed to have 2 nodes here from the constraints. So now we could say while fast.next, we could just move them both up, right? So slow equals slow.next, and then fast equals fast.next. Now remember we want the like new head of the list or whatever you want to call it. So we can just say that, call that like head2 or something, equals slow.next. Now we want to break that gap between the lists. So slow.next equals none. Now our 2 lists are split in half. Then we want to actually make a previous, and we want to do a list reverse on the list starting at head 2. So we could say, how would you do a list reverse? It's pretty straightforward, right? So we could do like while head2 temp equals head2.next, head2.next equals previous, previous equals head2, head2 equals temp. And so now the new head of the list is going to be the previous because the head is going to be out of bounds, right? So when you do this, the previous starts off behind, and then the head2 is going to be over here, and then the previous is going to be here. So now previous is going to be the name, or it's going to be the new head of the list. So now all we have to do is we can just say while head, all right, the head of the original list, we can just compare the values. So we actually need somewhere to store this in. So let's add that somewhere. So we can just say result equals like 0 or something. We're going to try to maximize it. I think it's only positive numbers. That's fine. So we can just do while head. We can do result equals max result. And then you're adding the two nodes. So you're adding like when you have these two lists, you are adding both of these values, right? So we're going down them and we're adding these two values, these two values, these two values. Okay, so that's going to be head.val and previous.val because previous is the new head of the list. Now we simply move them both up. So head equals head.next and previous equals previous.next. Let's make some more space here. And so now finally that we have that, now we should have a maximum result value. So now we can just return the result. Let's take a look if we did anything wrong. Okay, here we go. So why is this printing that its none type has object val? I think our previous is like getting out of bounds too fast. So let's just double check our code really quick. Okay, so let's see. I think this part should be fine. Slow, fast, that part should be fine. Slow equals slow.next. Oh yeah, so this fast needs to move up twice, right? The fast pointer needs to move up twice. So let's try that. Okay, let's see what happens. Output 5, expected 6. Okay, that's interesting. Let's actually print the previous and the, so print head.val, prev.val maybe, just to see what we have here. Okay, 5142. That's correct. Oh, right, they need to add them together. Okay, there we go. Okay, perfect. And so there we go, and now we can take out this print statement because that probably slows it down as well. And we should have something reasonably efficient, and we do. Okay, so now let's think of the space and time complexity here. So what are we actually doing? For most linked list problems, they're mostly going to be O of n complexity because you're essentially iterating through the list once. So it's going to be O of n here because essentially what we're doing is we're getting to the halfway point and then we are reversing the other half of the list. So getting to the halfway point is O of n, and then reversing the list is also O of n. So this is O of n, and this actually we're reversing here. So this is O of n as well. So this is going to be O of n, and then iterating through the halves of the list are O of n, right? So these are all O of n, so that's going to be O of n for the time. So time is O of n. And for space, we actually did all of this in place, right? We didn't create any new nodes. And that's going to be super common for linked list problems. I think this is the most common time in space. You're usually just swapping pointers around and you're not creating new nodes. And so that's going to be O of 1 space. So hopefully you liked this problem. And if you did, please like the video and subscribe to the channel. And I will see you in the next one. Thanks for watching.